tarde a todos e a todas. Meu portunhol é não muito bom, então eu vou falar no inglês. Hello everyone. Thanks for the invitation, for coming to here to show my recent work. And I think it goes on extremes, and I think it fits quite well with the work that you do here. Probably many of the topics you know better than me, but I will be showing. But we can share different ideas, and I would be very happy to take on board your perspective as well. I start with this very abstract art. It's called Sonhos Riverino, e de um artista brasileiro. E é porque eu vou falar da Amazônia. Sorry, I jumped to Portuñol. So I will be talking specifically about the drought and temperature extremes this recent year and ongoing year in Amazonia, with this exceptional El Niño. And this, although just my name is there for simplicity, this is the work I have been doing with colleagues from France, from England, from Spain, from Chile, from Brazil. So it's just the tip of the iceberg. And the outline of this talk is I will start with some features and global impacts of this El Niño event in 2015-2016. Then I will show you something more specific to Amazonia, how was the impact of this event on the Amazonian climate. And then I will end up showing, because the story is still not complete, we are still seeing the effects of this El Niño event. And so you cannot conclude how extreme it was. So you can say something about how extreme you think it's going to be. And so I will end up a bit giving some projection of how it will look in the river levels, in the water in Amazonia, how extreme it will be. A bit about my research. So I work with climate and ecosystems in simple words. I did my PhD, I finished in 2013-14 in the climatic research unit, this little tank that you see on the top left. And that's a little unit in a corner of England, and that specialized on producing the grid climate data that most of you might know. And then I moved to the LSE in France, the green symbol in the bottom left, Laboratoire de sciences du climat dans l'environnement. I have problems now with losing my French, my little French. And then, so this was a postdoc I did there, joined with the University of Leeds in England. That was for the last 2 years. And then I moved to Chile to Center for Resilience and Climate Research. That is a multi-university center that was created a few years ago. And then on the top right, I have a bit of a Google Scholar profile, so you have an idea of if someone wants to look at my recent work there. I have a profile updated with all the recent publications that I have been doing with my collaborators in these 4 institutions. Then I will now start with El Niño. So El Niño is a natural climate anomaly that occurs in the tropical Pacific that basically arise from the coupled dynamics of the ocean and the atmosphere. And it is characterized by, in the top part of the slide, you see the normal conditions, which is very hot near the maritime continent, and then a cool Eastern Pacific on the right, and then you have a circulation pattern, ocean atmosphere circulation pattern, and then you have a lot of convection on the maritime continent where it's hot, and then you have the descent of warm and dry air in the Eastern Pacific, so it's very dry. But then all that changes when an El Nino event occurs. Everything moves towards the Eastern Pacific, the warm part. The winds change, and then that change in the convection and the heat in the ocean affect the global climate, especially the circulation in the tropical band. So these events occur about 2 to 8 years. Peak the maximum temperature warming peak around November, December, and last for about a year. And then when one of these warming events occur, then it tends to be followed by a La Nina event, which is a cooling, which is the reversal of that, and more enhancing of the normal condition. That would be a La Nina effect. So that's well-known cartoon, and I think El Nino is very well known in the climate community, and even in the news, people now talk about El Nino like a normal thing that everyone understands. So because it's such a big change of the normal pattern of circulation, so it has global impacts. So that's another cartoon from NOAA where you see that basically a wicked upwelling and an altered ocean current affect the marine ecosystems and fisheries. So El Nino is well known in the coast of Peru because it warms a lot, and then the fishes die, or the catch is very low. And so the fishermen there know well that basically when it comes near Christmas, because it occurs in November, December, the peak, you have no fish there, or very little. And then the shift in the rainfall, that has a big impact on terrestrial ecosystems and agriculture. So that's the bit that basically affect us, the humans, living on the continent. And then you see there on the cartoon, you see a lot of, some regions are with a green color in the map. That is where you get a lot of wet, so floods usually, and that is in La Plata Basin, in northern Argentina, southern Brazil. A bit further to southeastern Brazil, you have a lot of worm there. And then what is well known for all of you is that it's dry in most of the northern part, northeastern Brazil. And then Australia is very dry. Also Africa is very dry and warm. Some combination dry and warm are not good for the ecosystem because you have a lot of fire. No? It's the ingredient, one of the ingredients for fire. So both the marine and terrestrial ecosystems are affected by El Nino. And then we tend to think that El Nino is just one thing, one pattern of circulation, but it really varies. Different El Ninos here is a special from the Bulletin of the American Meteorological Society, special on different phases of El Nino. So different events have different features, and the maps you see there are sea surface temperature. So the more red is hotter. You had the event, for instance, was 1982, 1983, which was one of the strong El Nino events, and then you have another 87, 88, which was sort of weak, and then 98, that's the second, is the strongest now event until the recent one that we had. they will vary in intensity, and sometimes we expect something and we don't get what we expect. Or we expect one thing and we get another. And then, so because this El Nino event was expected to be 2015, 2016 was expected to be or projected to be even warmer and more extreme than the 1997-98 event. So there was a lot of research about that, and it was in the news, and so it was a Godzilla Nino call as well. And then every year the Bulletin of the American Meteorological Society produced a report which summarizes the state of the climate of the previous year. So this was released in September, in August, and so we were in different sections. The people from different institutions in the world contribute to different variables. So they focus on what is called essential climate variables. And there is soil moisture, there is some indices of vegetation, there is drought, there are, name it, many, ice as well, variables. So it's a summary for many types of variables of the climate system. And so you have then the groups all over the world working in one section of that report. So it's a bit like an IPCC, but for every year. Let's say it's a little cousin of the IPCC report. And it reports on usually people is making an in-house update of the data set to produce a complete 2015 picture, but that picture is not too robust because there is quite a big lag for the observation to arrive to the centers. So usually this snapshot you get is with incomplete set of observations. So that's good to keep in mind, but it will give you a very good idea of what happened, how anomalous it was this year, and they have also some emphasis on the extremes. Yeah. So then the climate of this year, 2015, was marked by El Nino. So, and it was quite exceptional because this El Nino basically results from a combination. It has a warmer background than the 1997-98 El Nino. So the Earth was warmer on average now than then. So that plus the natural warming that occurs in the Pacific amplified the impacts. So that's why it's one feature why this El Nino was so exceptional and particular as well. So it's not a flat background in temperature, it's warming, and on top of that warming, we had this El Nino. And then there is a representation of artistic representation. I think it was the daughter of one of the contributors. And there you have a fire, you have temperature rising, I think it's CO2, and you have also ice variables. So that represents a bit. And then the top, of course, is the atmosphere represented there, all trends. So I will revise a bit how was the snapshot in different variables of the climate system. So warming first, we see that for the period, this is a summary of the global temperature record from the Climatic Research Unit. And then you see that 2015 in the top right, 2015, 2016 is just really above everything in the last 160 years. So it's 0.8 degrees Celsius, or almost 0.9 degrees Celsius warmer than the base period 1960-1990. So it's a very warm year. And then the question is, if you see the temperature record since the 1950s, there are some steps in the temperature. So in the 50s, from the early 1900 to the 1950s, there was a going up and then a plateau. Then again another step since the 1960s, around 1970s, until the 2000s, and then a plateau. So the question is now, are we going to have another of these warming steps? There is no way back there. We don't go, once we go one step up, we don't go back. So that's an interesting question, and we will know just in the future. or with models. But so it's like, what will happen? One question is now, what will happen with this little dot? We'll go down to the around 2000 level, which is called the global warming hiatus, which was basically no warming in the global average. And so that's an interesting point. So we see that 2016 is record, and the story is still ongoing. And then in drought, this comes from the section of the BAM's report that I showed you before. So this is that we do it every year in the climatic research unit. We produce a drought index, which is called self-calibrated PDSI, Palmer Drought Severity Index, which is an index, a normalized index of what will be a proxy for soil moisture. So negative values means dry, and positive values means wet. But here, what we do is we count all the area of the Earth for every month since 1950 to 2015, which was under moderate, severe, or extreme drought. So we focus on drought here. So red is the area under extreme drought. That is basically you have, by construction, the index has only about 2% of the month of the total period for a given grid box that will have that category. So it's an extreme event. Okay. So and then we see that the area of the globe in 2015, which is just the full right on the plot, on the big plot, we see a peak in drought. So the areas under drought expanded in 2015, as you would expect because of El Niño. But then you see that this peak is larger than the one you would see in 1997, around 2000, when there is a little dip. That was the other biggest El Niño event, and it didn't have so much drought. But now this event does have a lot of drought, and is similar to other years in the 1980s, which globally were quite dry for different reasons. But so we still here don't have the complete picture, because the impact of El Niño, it was there October, November, December is the peak, but most of the impact occurs in the months following that. So like, let's say June, July, August 2016. So the picture is incomplete, and we don't know if that peak went up still and overpassed the ones in the 1980s, or it went down. So that's again another interrogant. But what we can tell is that at least until December 2015, it was a very, very dry year. So you had an expansion of dry areas. But although not unprecedented as the one in the 1980s, still. Then in vegetation, 2015 was also a particular year for the Northern Hemisphere. You see the top plot A, the green, that's the anomaly in greenness, which is NDVI from MODIS. So this is from, you see in the panel C there, the Northern Hemisphere NDVI average in standard deviation. So from 2000 to 2015, you see that basically in the right top, you have 2015, an extreme value of greenness. So it means more photosynthesis in the land surface. This vegetation was very active over the growing season. And then on the panel B are for every year you make a histogram, let's say, of the NDVI per every grid box, and then you see the green line, 2015. So you had a lot of, it's really the only one that goes up to 3 standard deviations. You have a lot of area above 2 standard deviations in positive, so it means there was a lot of greening. And that has to do with a lot of warming as well. So because the Northern Hemisphere is the boreal forest, usually tend to respond positively to temperature, so that is a bit the result of warming. So it means that vegetation is still tracking the warming, but there is not always just one there are several shades of gray there. And in some areas you see in the anomaly in Europe and Eastern Europe, Central Europe, you see sort of reddish color. So it means that there was less greenish than normal there. But even though in the hemispheric average, you have a lot of green. So exceptional vegetation activity in the northern hemisphere. This is a research that I'm collaborating with people in LSE in France. It's submitted. And then for the ecosystems, let's say if you want to see the response of the biosphere, all this, again, another record is that one way to see the response of the biosphere to climate and to the human activities is to look at the growth rate of the atmospheric CO2 concentrations. So is a change in growth, and that growth depends on how much ecosystem capture, sequestrate carbon, take carbon from the atmosphere, and how much the humans and also the same ecosystem release. So it's a net balance. And then you see that there were years where 1997, around the 2000 there, the little bar, it was 2.93 ppm in 1998. It was the year. So the year after El Niño started, and that was the very, very extreme. So there was a lot of CO2 basically in the atmosphere, pumping in, more going in than coming down. So, and that is due to big fires in Indonesia, in the tropical regions in 1997, peat fires, and especially big contributions. And now we have 2015 again in the right corner, which overpassed that. So now it was 3.05. So we went above 3 ppm of growth. So it's bigger than the previous record that we had. So again, record broken. So that means that the ecosystems in a way were a source, and plus the human activities on top. And that it goes into likely produce more warming because you are injecting more CO2 to the atmosphere faster. And then now I'm just narrowing down. That's the global picture. Now I will narrow down for Amazonia, and we had the good fortune with some colleagues from Spain, Chile, England, and Peru, and the Netherlands, that we were sort of working in parallel, and then we said, okay, we're looking at the variables now. Why we don't look at this, what's happening with this El Niño? We have updated data, so let's have a look. And then, that ended up in this publication in Scientific Reports. It was published like 2 weeks ago. So it's very fresh from press. And the title says it, record-breaking warming and extreme drought in the Amazon rainforest during the El Niño 2015-2016. And so everything is summarized in two figures. The first figure is the top panel A, is the average temperature for Amazonia, and this is from the reanalysis. We use reanalysis error interim temperatures fields because we wanted to have the spatial map as well of spatial temporal variability. And we checked and we found that error interim does a good job for the region that we were studying. So we believe it to a certain extent. And then we look at the skin temperature. So that is really the surface temperatures. So you see in the top panel that you see one peak in this is monthly temperature anomalies for average over Amazonia. So you see one peak in 1982, 1983, then the peak in 97, 98. Similar. You see the little black line is similar, and then you see a bit of a jump of warming after 1997 to another level, like another step in the stairs. And then, again, like I showed for the global temperature, you see the big jump in 2015, where you see some gray up to 2.5 degrees above the mean. So it was a very big extreme, so it was very hot. And somehow, what will happen after is a good question. And now, in the top panel again, the little inset there is the temperature, the profile, let's say, from the year before El Nino started to the year after El Nino ended. So you have 4 years, I think. So for the gray line, brown line, there is the current El Nino, so the one that's on top. So you see, it says Amazonia, and then you see year 2014 should be the 0 to 12, 12 to 24 is 2015, and our analysis ended in March 2015, so it's around 26 months, 26. You see that the peak was larger than the other two previous strong El Niños, 1987 and 1982. And you see that the 0 to 12 or 0 to 24, it's up the other, so that's the level of warming. So that we were in another level now. So it started from higher, let's say, that El Nino. But in overall, make it much extreme, much warmer. And on average, 1.8 or 1.7 degrees Celsius above the mean. And I would say about half a degree, a bit warmer than the 1997 in the peak time. Then panel B, it shows the sea surface temperature plus land surface temperatures for October, November, December for 1982, then in the middle 1997, and then 2015. So that is the time when El Nino warming in the Pacific Ocean is peaking, yeah. When the fisher find very few fishes in Peru. Then you see that the current, the 2015 El Nino, the warming was more centered towards the Pacific, the Central Pacific. You see that 1997, 1992 are all along and reach even to the coast of South America. And then you see also that the 2015 is overall warmer everywhere. It's because we are in a warmer state. And then you see over Amazonia, over Brazil, a big red spot. So that's at the time when El Nino was peaking. So about 3 degrees Celsius, some places 3.4. And then January, February, March, right on the right panels there, the maps are right after El Nino peak. And then again you see that 2016 was sort of, it faded away quite fast, the warming, but it was much warmer in the Central Pacific. And that difference with the others is quite important, because if you warm a bit more the Eastern Pacific or the Central Pacific or all along, has different impacts on the global circulation, and then the impacts on land or the oceans will be different as well. So let's say that the conclusion here is that this El Nino has a different character than the two other strongs. So it was strong, but it has a bit of a different character. And then we are going to look at how it impacted. And then here, figure 2 is the impact that it had on drought. So I explain you again, is the same map that I show for the global, the same index. But this is computed now with the interim data. And then again, I show the drought, the extreme drought and severe and moderate drought areas for every event. So in the panel A, in the left, 1992, 1983, so 24 months. Then you see that, for instance, at the time of the peak of El Nino, you have very little drought in Amazonia. So let's say September, October, November. So the drought peaked the following year. And then it's the same for 1997, 1998. And then we have the 2015, 2016 until March. So then we see, when we compare the three, we see that basically 2015 and 16 had a bigger area of extreme drought. And whilst the other categories was not too exceptional, but it has much more extreme drought. So, and then on panel B are the maps for January, February, March drought. Still, it's not the time when drought peak, because drought peak May, June, July, let's say. And we didn't have the data updated there, so we got the more close to the present we had. So again, you see the 1983 effect on drought. So almost all northern Amazonia, it's in red there. So it means from moderate to severe and extreme drought. And a bit, you see some blue there, which is towards the southern Brazil, which is where it gets wet. But then you see 1998, you see again a similar pattern than that you saw in 1983, but a bit more towards the displaced towards the center. So, but overall, canonically, is similar. And then the pattern for 2016, which is quite different. So there we see an overwetting in the western Amazonia, northwestern Amazonia, and a lot of red, dark red in northeastern Amazonia. So where you expect that usually it will be dry, it was very dry this year, but it was much drier than the previous years. But this west-east dipole was intriguing us, and we thought it was a problem of the data. And we look at the things, and then we look at GRACE, and GRACE also showed the same. GRACE is this satellite-derived estimate of the water mass over land, and which is completely independent and is quite trustable over Amazonia, and it also shows the same pattern. And we look at the satellite and the station-based grid data set. Again, they show this pattern. So this was January, February, March, but now the picture changed. And so Liana was telling me about Acre. So Acre there is a bit in the south. There it's a bit on the wet area, I would say. But that changed somehow. And then, so that would be the continental picture, because before I was just showing Amazonia, the area of rainforest, but now I show you the whole South America, let's say, subtropical and subtropical. And then you see that this wet dipole that we saw over Amazonia runs to the south and goes to La Plata, where we expect that it's very wet for El Niño. And there it was as we expected, so it was very wet. And then you see, but this very diagonal there is quite striking, and so we are still trying to understand. And then I plotted a bit. I wanted to see how this, because this index is a proxy for soil moisture that correlates with soil moisture and also with river runoff. I wanted to see if the river runoff would also tell me the same dipole. So I plot there the the network of water levels, river levels, and I standardize them so they are a bit similar in units. You cannot really see the points there much, but in Amazonia, in the area where it's blue, the little dots tend to be blue too. So it tells you that actually it seems that it was a true dipole, and that the runoff there, at least at that time, was above the average. And then you see also in the northeast, you see that the little dots are also red and similar color to the background. So it also the anomalies were negative. So it seems that by that time, what we saw with this gridded data, reanalysis data, made sense in reality. So it was a bit of a reality check. And then there is another feature there in Chile. A little bit appears there. There is a gray area there in the west coast where the Atacama Desert is. So right above the desert, below the desert, you see some of Chile. And there is a drought. It's called mega drought. René Garreau, a colleague from Chile, he called it mega drought. I was a skeptic at the beginning of calling it. It's a very American term, and I thought, okay. But after doing analysis, I think it's in the context of Chile, it is a mega drought. It's a very long drought. It has lasted now for 7 years. So it started in 2010, so 6 years is going to be 7 years now. And then there was this El Nino. That area where it's red, you would expect it to be blue, but it didn't happen. So El Nino it didn't bring the relief for the drought. So there is a big concern now with those droughts in Chile. What is happening? What is causing it? And so the center where I work, there are very lot of research on that, and there is a special issue in a journal as well now where we are working with René in different aspects of this drought. So in a way, we are looking at similar things as well in that region, part of the world. And that little red there actually is more important than what it looks like, because it's an extension of the ocean. Because there is, in the Pacific, southeastern Pacific, there is a big band that is drying. And there, in the continent, you see a sharp contrast, like running along the coast between blue and in Argentina and red in Chile, because it's the Andes. The Andes blocks the western flow. So that's why you see that sharp contrast. So basically what we see on land there is an expression of a much larger pattern of climate change that is happening in the South Pacific. And then now, how dry we think that 2016 will be? So I took the daily water level of the Amazon River at Óbidos, and then that is from 1970, and I updated to the 20th of September, so last week. And then I completed it until you see there in the red projection, October to December. I use a statistical method that basically models the annual cycle and the cycles somehow in the time series, to project it to December of 2016. So the little red that you see. And then I draw a line, the blue line, at the 2.5 percentile of the daily value. So that tells me to define the extreme event. Anything below that threshold is something event very rare, so it's an extreme. Then you see something around 1995, 1997, 98, 2005. You have 2010 there. And then you have 2015 also crosses, and then the red, my projection crosses there. So it tells that it's going to be a bit worse at 2015, the dry season that is happening now. But there is a better way to look at it. So we can extract the events that we saw there, and we can define the duration and the intensity. So the intensity is just the minimum level that you reach in a run of daily values below this threshold 2.5 percentile. That's what I would call drought here. So then I will get a duration and an intensity. And then I plot here the duration in days in the x-axis, and in the y-axis is the drought event minimum water level. So that tells me the minimum that was reached in that event. So you see that the minimums somehow are negative to the top. So as you go to the top, it's worse drought. And then, so you have in the map, in the plot, the top right corner, it tells you that the most intense drought and the longest drought, it was the most intense somehow, it was 2010. So you got a stage level about minus 0.6, I mean, at Óbidos. And that drought lasted for about 2 months, yeah. And then, but the most extreme until now is 1997, and the most, I'd say, the longest drought, and it's a bit less intense than the 2010. And then you have to 1995 too, another drought, and then 2005. So you see these big droughts that have been in the media a lot. They map over there. And then if we consider my projection, 2016 should be the pink line. So I would expect a drought with a length a bit more than 2 months, to almost 2.5 months, but not too intense. So it won't be as intense as in the 2010. But in overall, it should be in the top 4 droughts that have occurred in Amazonia since the 1970s. We will see if this projection occurs, but then there is a little gray cross where more or less you would expect it to fall. So, but still will be, I think, one of the top 4 extremes. And so that's a bit what I have to show, and then just a few take-home message. And the first take-home message is that globally the 2015-2016 El Niño event was different than previous strong El Niño events. So it has more warming in the Central Pacific and occurs over a state of the Earth when it was warmer than in the previous strong events. And then the climate anomaly. That's why the climate anomaly during 2015-16 broke many records. We saw it in the atmospheric CO2, in greening, in temperature, and in drought. We don't know yet. Then the third take-home message is 2015 was the warmest year on record in Amazonia, at least over the last 40 years. We don't have reliable records for before much that represent the entire basin. And had the highest extreme drought area among the strong El Niño events. But having said that, there was this strange wetting in Western Amazonia that perhaps helped to ameliorate the impact on the river levels that I was projecting. And then the projection is that this 2016 now will likely rank as one of the top 4 droughts in Amazonia. So that would be a bit the projection. We have a bit of few months to go to reach the minimum in the dry season, and then we will see what happens. And then, muito obrigado por sua atenção.
Muito obrigada. Vou abrir para perguntas agora. Vou fazer uma pergunta então. Realmente chama atenção aquela parte mais úmida no sudoeste da Amazônia, e principalmente quando a gente contrasta um pouco com os relatos de campo. Talvez o Conrado depois possa falar, o Conrado Adriano, né, um pouco do Madeira, do que aconteceu em 2015, né, que acho que vocês acompanharam bem de perto. E entrando com a estação seca agora naquela região, a impressão que eu tenho e do que a gente conversou com o pessoal no Acre é que realmente essa recarga, pelo menos para a vegetação, ela não aconteceu. Porque você veio de uma estação chuvosa que ela já foi um pouco abaixo da média para aquela região. Então a estação chuvosa não foi tão forte, já vinha com um pouco dos efeitos do El Niño, e quando começou a estação seca, agora em junho, julho, agosto, realmente os impactos foram amplificados, não só pela seca em si, mas pela questão da temperatura, que você também apontou. Então, em termos dos impactos na vegetação, por exemplo, os agricultores, eles reportam que teve perda das árvores frutíferas, e até o entendimento por que eles estão perdendo as árvores, por que eles estão morrendo, se você está tendo a perda de produção, né, se é um ano de seca. E aí vem os dados de temperatura realmente para trazer essa informação complementar, né? Então a gente não está falando de um impacto único, são duas forçantes combinadas. E aí tem os impactos diretos, né, no caso a perda de produção, tem os impactos indiretos, que é a ocorrência de incêndios florestais. A estimativa de área queimada que eles estão fazendo lá para o Acre é muito próxima a 2005, que foi o ano que teve os maiores incêndios florestais lá na região. E E os impactos indiretos das queimadas, né? Então, você tem toda a questão da poluição atmosférica, o número de pessoas sendo internadas por problemas de saúde. Existe até uma discussão local de quem é a fumaça. E essa discussão estava na mídia toda semana, né? Uma parte do governo atribuindo toda essa fumaça. As queimadas que estão acontecendo de forma anômala também. No Peru, na Bolívia. Então, dessa fumaça está vindo de fora, não é nossa. Mas os dados ali contrastando, mostrando que você tem toda essa queimada. E como você teve essas queimadas, essas secas, com também muitos incêndios florestais em 2005 e 2010, e agora em 2016, as áreas que queimaram em 2005 e queimaram em 2010, quando você vai ver a característica que elas estão no campo, lá você tem a presença de florestas de bambu. Então você começa a ter uma alteração da composição de espécies muito rápida nessas áreas. A Sonaira, espero que ela possa vir aqui dar uma palestra para a gente nos próximos meses, ela trabalha com esses inventários nessas áreas. Ela fala, olha, essas áreas foram queimadas uma ou duas vezes e que queimaram agora em 2016, eu não consigo nem atribuir a elas como floresta. E a gente não tem uma nomenclatura para isso, porque não é uma floresta secundária, porque ela nunca foi desmatada. Mas por causa do impacto de fogo, você mudou o status daquela floresta, a característica dela. Então, como você disse, né, eu acho que ainda tem diversos desses impactos ainda estão surgindo. Tiveram problemas de abastecimento na cidade do Acre, tiveram que vir com um plano de contingência, acionar as bombas para conseguir ter o abastecimento da cidade. Então, assim, os efeitos desse El Niño, eles ainda estão aparecendo e tem a expectativa, né, de quando vão começar as chuvas para amenizar um pouco os problemas. E se essas chuvas não vão ser extremas também, porque o que tem acontecido no sudoeste da Amazônia, ou eles estão embaixo d'água ou eles estão, né, embaixo de fogo, por assim dizer. Então, como que a gente se prepara? Quando a gente está embaixo d'água, a gente começa a se preparar para apagar os incêndios da estação seca. No meio da estação seca, você está com toda essa situação crítica, você tem que se preparar para a cheia que vai acontecer. Então, é bem apontado, né? Você está falando de todos os anos, aí você está tendo quebra de recordes. Naquilo que você se propõe a medir, se você começa a fazer umas análises, você encontra esse tipo de informação. Então, realmente é bastante dramático e a gente está mudando, né? Você falou dos steps, né? Dos degraus, parece que está tendo realmente uma mudança no platô do que a gente considera como comum ou do que a série histórica sugere que seria o esperado, né?
It's like when you break a record, you enter to a completely new level until you break the record again, and so on. And for the case of this dipole, I was a skeptic of it. I thought it could be an artifact of the air interring, but it's also in grace. So I think it's an effect also of seasonality there. And when we look at the river level, the wet season of 2015, it was low, at least at Ovidus. So it tells you that in overall there was less water than normal there in the wet season. But still, I think there is a big effect of there is a limitation on my index on one side, and then a big effect of the atmosphere, the warmer and drier atmosphere on drying the land surface. So that feedback, I think it's very important, as you were saying, and probably it's very different than the previous years or the previous extremes that have been. So it's something that is emerging.
I was curious about the projection of the for the 2015 low water at Obidos. What was the method you used?
It's a spectral method. It's called multi-taper method, SSA, singular spectral analysis. It's a UCLA group that they work with this spectral stuff. They do it to reconstruct El Nilo, let's say, El Nilo River. You have some data, and then you have a gap, and then you have more data, and so you can extract certain periodical signals, and then you know that periodic signal is predictable, and explain a lot of variance of your time series, so you can you can somehow, it's because leads and lags. You can actually predict itself, let's say.
And the input data is just
The time series.
The time series.
Yeah, yeah. It's also called multi-channel. You can do spatial constructions as well. So it's basically it's by the memory embedded in the same time series, so that the system is predictable. So one cycle that's predictable is the annual cycle. If you have an annual cycle, that's very predictable. Then you might be having a decadal sinusoid as well, that's predictable. And then you might be having a trend that's quite predictable. And perhaps if you are able to predict those, you can explain, I don't know, 60% of your time series or 70%. So that's how it's purely statistical, based on the memory. Yeah.
Você comentar alguma coisa do nível dos rios? Agora que...
Então, eu não estou acompanhando Madeira e o Acre. Eu não sei como que foi janeiro, fevereiro, março. Mas o que eu queria ver, dá para mostrar de novo a apresentação? Puedes volver a la...
Ah, hablas español. ¿A cuál?
No demostraste que está greening y el CO2. Entonces, aquí tú mostraste que tuvo más greening en el hemisferio norte, ¿cierto?
Sí.
Y solo el hemisferio norte y en el hemisferio sur sabes que pasó nada. Ahí tú vienes en la otra. Ahí muestra. Entonces, aquí tuvo más y tenía más fotosíntesis. ¿De dónde que está viniendo ese CO2?
Los trópicos. Trópicos y probablemente the tropics and probably the southern hemisphere. Yeah. Yeah.
Una cosa no está...
But also this was until so it was 2015. So it was whilst the Niño was warming. So it was April, May, June, July, August, September. El Niño peak in September, October, November. So again, the picture is a bit late. Yeah. And perhaps I can tell you I have some bonus, but it's nothing related with the talk. No, it is a bit, but it's about what I am doing now, like in my main dish, let's say. It's because I do climate analysis, but I am interested in ecosystems as well. And I have turned a bit now I want to become an ecosystem modeler. It's a hard path, but I'm going slow. So in my current postdoc, which I am now like 5 months in, and it's 2 years, so I have 1.5 years to go. With this, I want to compare, so I want to model carbon and water ecosystem services and the climate and land use change. So for that, I chose an area in southern Amazonia and also in the Valdivian rainforest ecoregion. So the trick here is that what's common between the two is that the two are very rainy. There it rained like 3,000 millimeters, and similar to what you would see in part of Amazonia, let's say. And also in Chile, you have a lot of land use change. First you had a lot of native forests. It was cut, prairies, grassland perhaps, and then they put forest plantations there, eucalyptus and pinus, or they had native forests and then they cut and they put a plantation directly, and that's a lot. And now when you look at it in the satellite, that would look like a regrowing of forest, all those plantations, but actually it's just, it's not real forest. And so then there is a lot of problems now with water, because you basically, it's like you put a big pump from the soil to the atmosphere. So they planted species like complete landscapes of eucalyptus that grow very fast and transpire a lot. So you dry the soils, and they dry the creeks. Now there is no more water, and people that they had water, usually they made a hole on the ground and a well, and then they will get water. But now they don't get water, so the groundwater went down. Plus it's drying, and so bad combination. So that's why I'm interested in using in modeling the ecosystem services. It means basically that what I want to do there is I can simulate an ecosystem. I have a model that simulates the ecosystem, and and this is the French model. It's a French global ecosystem model called Orchidée, but this is a special branch of that model that simulates forest structure. So it's not really like the big leaf models that you have only one tree, a model tree, and that everything happened to that model tree. Here you have a full distribution of trees, so you have many model trees, let's say, and then you to compete them, to growth, to allocate. So it's a very nice dynamic, and then you can grow forest stand over time, and then you can somehow simulate the water and the carbon, and that's what I am interested. So I want to apply this model to answer these questions of how long does a forest take to recover the water function and carbon function than a mature forest, let's say, and in two environments, one tropical and one more cooler temperate. So that's a bit the research where I am now, and where I would be very happy to collaborate with you is that I am looking for forest structure data of canopy or forest structure or forest inventories or biomass that I could use, and we could collaborate in using with the model as well, to calibrate the model and to test the model. So if you know colleagues that could be potentially interested in that, I would be very happy that you let me know. So, or yourself, if you want to collaborate on this. And we are still finishing some developments in the model, but it's ready, and it's going to be the next model for the AR6, the 6 assessment report. And they will add nitrogen too, so there will be a merged version, nitrogen, carbon cycling, you have the water cycle, and then on top of that you have this forest structure. That makes that this model will be basically at the cutting edge of the global models, because the other models are quite simple in the way to be able to be globals. And this is a step towards more sort of individual-based models, but it's something in between. So it grows like population structure models. There are models for fish in fisheries. They use these sort of population structure models where you have certain amount distribution, what you prescribe the distribution of individual. Usually you tend to have a lot of little fishes, let's say, or a lot of little trees, and few big ones. So then you can prescribe that distribution, and then you let you grow forest. So that's a bit how it works. That's a bit comes out of the blue here with the other context, but is what I am basically working on now. Yeah.
But there is a big similarity here, especially when you move from the structure to the service cascade.
Mm-hmm.
Because then you're talking about, we have all the environmental function, but we have the service and the values, and we have to add this to show the link with the social and economic system.
Mm-hmm.
And understanding the function and the services, and to understand how it looks now and what would be the impacts, for instance, of such a drought, is of interest for us.
And those are applications, that one can do with this setup. Yeah, exactly.
I think we can think about how we can use what we produce.
So it would be fantastic to envision collaborations on these lines. It's a fantastic tool, but also you have to have good questions, and I have some questions, and I know that whilst I'm pushing those questions, I likely will get interested in other questions that appears as more interesting in the end. So I'm very happy to collaborate with any of you that want to work on this.
Do ciclo do nitrogênio também? As mudanças no ciclo do nitrogênio?
Agora eu não I didn't envision to use it, yeah. Mas pode ser que se eu comece a trabalhar se a versão do modelo fica completa agora, pronto, eu posso usar também nitrogênio. Então, depende um pouco dos timings da gente. Yeah.
How does this model do with wetlands? Does it,
Very basic, I think. Yeah.
so would your analysis be more focused on headwaters or forest?
Forest, yeah. Basically, forest. In different stage of growth. Because I could prescribe also a landscape, and then I let that landscape grow. Or I prescribe the land use change. So I can get some variable of ecosystem service integrated over my landscape over time.
So then you wouldn't aim for a regional water and carbon balance, but rather focus on specific forest ecosystems.
Yeah, but it will be regional. Yeah, it will be a domain, let's say square domain in that region. But first, to get that, I really need to work at the pixel level, at the plot level, so that I make sure that the model is
to calibrate and
yeah.
make it very
Exactly.
the best you can to get the next step.
And then the next step is to expand it spatially. So that's exactly the task.
Perhaps the anisotropic data.
Yeah, I was talking to him before. Also lighter data then to get
And
close to the
so this is a This is a collaboration that we are doing with the I don't know if you have heard Sebastian Leiser. He took Orchidea traditional and basically rewrote many things and came up with this version that is very nice. And they had an ERC project in Europe where he basically asked what was the impact of forest management, of 400 years of forest management on European climate. And basically to answer that question, they really needed to work the energy balance. And to get at the energy balance, you really need to have a good canopy. And to really have a good canopy, you need to have a structure. So that basically led to the development of this version that actually will be very lucky as to build up on that. Yeah.
Obrigada pelo seu tempo, obrigada por vir aqui.
Thank you very much for the invitation.